Daniel Weiner, and I just want to explain my neural network project as a companion piece to the code that's on GitHub. So I made a neural network class in Python just to understand neural networks better as I'm learning more about machine learning. So I made this neural network class in Python without the use of any scientific libraries. You'll see I used NumPy, which I just used for storage options, Matplotlib, which I just used for visualization, and TensorFlow here is just to import the dataset because it's kind of a pain to actually download a massive dataset like MNIST and then have it. TensorFlow can literally just pop it in. So I'll actually search for TF. You see TF right there. So you can see that it's found 3 times here, and then it's found one more time down here where we actually import the MNIST dataset, but that's it. I never actually use any TensorFlow functions. So we have this sigmoid activation function defined here, and then we have sigmoid prime, which is just the derivative of the sigmoid activation function. Here we have the network object as a class. So the list contains the number of neurons in the respective layers. So basically what we do is we pass in sizes. So sizes, the length of sizes is the number of layers, and sizes equal sizes. The self.biases and self.weights is set randomly because it doesn't really matter because it will optimize as we run it, which you can see later on, but it will optimize. So we set it randomly for now, and then it optimizes. Then we have the feed forward, which is literally just the point of a neural network, is that it feeds through the neural network. So for BW, biases and weights in the self.biases, self.weights, A equals sigmoid NP dot weights. A plus bias, A is the input plus biases. So basically all it's doing is doing a dot product of the weights vector and the input vector A, and then it's adding the bias. So that's all a neural network is. It's a very simple thing, except obviously there's backpropagation and other optimization and elastic net, a bunch of other stuff that could be there. But when it comes down to the very basic thing, you can have a very basic working neural network like this. So we have a fit function. So this trains the neural network using mini batch stochastic gradient descent. Training data, it says it's a list of tuples representing the training inputs, but it's basically an optional input. You can optionally put in training data. As you can see here, test data. You can optionally put in. Oh, sorry. Okay, so I'm saying training data is the actual training data. Let me go through it like this. Training data is the actual training data. Epochs is the amount of epochs you want it to run for. The mini batch size is the mini batch size, how big you want the mini batches to be. ETA is the learning rate, and test data is an optional parameter. So if you do put test data in, it will tell you how accurate you are getting by using evaluate. I believe it uses evaluate. Yes, evaluate. So it uses evaluate in there. If you put in test data. If you don't, it will just print out the epoch. So I mean, there's really no point not to put in test data because you want to see how you're doing, and especially if you want to know if you want to stop at a certain point or when the network was best trained. So basically, it just goes if test data and test. Okay, so if there's test data and test equals the length of test data, n equals the length of training data for j in range of epochs, random shuffle training data, so it shuffles it randomly, and then the mini batches are the training data, k plus mini batch, k to k plus mini batch size for k in range 0 and a mini batch size for mini batch in mini batches, self.update mini batch, which is right down here, mini batch and learning rate. If there's test data, it'll print the epoch. It'll print epoch, the word, and then it'll format J, which is the actual epoch that you're currently on. Self.evaluate test data, which is the first one. So that'll be the evaluate function. Bam. That's going to give you the how many of the test data you are getting correct. And then end test is how many is in the test data. So like you'll see later on, there's actually 10,000 in the test data. So when you run this, it'll be like, oh, you're getting 5,000 out of the 10,000 right. So it'll be like epoch 2, 5,000/10,000. Epoch 3, 7,500 out of 10,000. Epoch 4, 9,000 out of 10,000. Then it slows down, So, and if you don't do that, if you don't put in test data, there's almost no information. But sometimes you don't have test data, right? What are you going to do? Mini batch, which takes in the mini batch and the ETA, updates the network's weights and biases by applying a single step of gradient descent using backpropagation to a single mini batch for each call to backprop. The mini batch is a list of tuples XY, and ETA is the learning rate. Nabla B and Nabla W are just temporary NumPy arrays in the shape of the biases and the weights with just zeros in them. So we make a for loop with the inputs and the outputs of the mini batch, and we invoke the backpropagation algorithm, which is a fast way of computing the gradient of the cost function. So we get the delta of Nabla B and Nabla W by doing the self-propagation with putting in the input and the output. And then we just add the delta and the current value that's in Nabla B and Nabla W. So we just keep adding those values and storing them into these lists, arrays, vectors, whatever. And then we just update self weights and self.biases, and that's how you update the mini batch, because you want to update the weights and biases. That's the whole point of this. The backpropagation algorithm is a little bit complicated, but the idea is to return a tuple, Nabla B and Nabla W, representing the gradient for the cost function, the CX, which is what's it called? The partial derivative with respect to x. Nabla B and Nabla W are layer by layer lists of NumPy arrays similar to self.bias, self.weights. So we have the same Nabla B and Nabla W NumPy arrays of zeros. We feed forward. So we have we basically feed forward. We have this activation variable. We have a list to store all the activations layer by layer, list to store all the z vectors layer by layer. So for the bias and weights in self.biases, self.weights, we basically do the feed forward activation. We append it. We put the activation through the activation function, which is the sigmoid function. We append it. We do a backwards pass now. So delta equals self.cost derivative, activations -1. So that's activations. This guy, -1, are less than the list, comma y. We put it through the sigmoid prime. We multiply it by sigmoid prime, zs -1. So sigmoid prime is the derivative of the sigmoid function. And then we update Nabla B's last variable with that. Nabla W's last variable gets updated with the dot product of delta and activations -2, second to last, transposed and dotted with delta. So this I did learn this stuff from a textbook, so the notation is a little bit different because he was using Python 2, so I had to change a lot of this stuff to make it work for Python 3. So this right here, you're just using L as a variable in range from 2 to number of layers. You don't want to use the input layer. So you go and you z equals zs negative L, sp equals sigmoid prime, so you're getting the derivative. Delta equals mp dot self.weights transpose delta. And then you update nabla b and nabla w, and you return nabla b and nabla w at the end of all that. That's the end of the backwards pass. It's a little bit confusing. There's a whole chapter dedicated to it in the book, so it is a little bit confusing. The evaluate is much simpler. You basically just pass in the test data, and the test results are the argmax. So it's just basically the maximum argument in a self.feedForward of x, which is the input, and np.argmax of y for x, y, and test data. This absolutely did not work. I had to rewrite this completely. His Python 2 version of this did not work at all. And then you return the sum of int x equals y for x, y, and test results, and there you get the value. So if you have 5,000 out of 10,000 or 9,000 out of 10,000, it'll tell you exactly how many you have right. And then the cost derivative, which will return the vector of partial derivatives. Partial cx, partial a for the output activations. It's just output activations minus y. That's all it is. So pretty simple. This right here, all this does right here is loads the data. So you have a function that loads data. So mnist, load and prepare the mnist data set. Mnist just calls tf.keras.datasets.mnist. We get xtrain, ytrain, xtest, and ytest, and we call mnist.load data. We convert the data from integers to floating point numbers because that's what the neural network needs. So basically they're all 255s. So we just turn them into, they're all integers, so we need to turn them into floating point numbers. From integers to floating point numbers. Wait. Convert the data from integers to floating point numbers. No. It's got to be from floating point numbers. No, it must be from integers to floating point numbers. Huh. Okay, so then we return those. This is to load the data wrapper 2. So we've got these guys. This is just a quick way of saying xtrain, xtest, ytrain, ytest calls load data, which is this guy. Xtrain equals mp.reshape. So basically what we're doing here is we're putting the, so what it is it's a 28 by 28, and what we need it to be is a 784 by 1. So the neural network can take it in as one. It can't go into the neural network as a square. It needs to go into the neural network as a single line so it can feed in. So we're doing that for everything. And we're also getting the argmax of the vectorized result for y, because y is the answer. So it's going to be a number between 0 and 9, and that's the answer of xtrain. So if xtrain is a 0, a handwritten 0, this will be 0. If this is a handwritten, it's actually going to be y is actually going to be an array like this. Sorry. It's going to be an array like this. It's going to be like 1, 2, 3, 4, 5, 6, 7, 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. And then if 9 is the answer, it'll be like that. Or if 8 is the answer, it'll be like that. So that's what that looks like. So we're just looking for the answer. So we get the argmax of the vectorized result. Vectorized results is just another function that I have. I'll go over it. And we just use the training data. We zip it into a list called training data. And then we do the same thing here. with the test, and then we zip it into a training data, and we return testing data and training data. Load data wrapper again. This was because I was having a little bit of trouble with this function. I suppose I got it to work. Vectorized result was returns a 10-dimensional univector with 1.0 in the jth position and zeros elsewhere. This is to convert a digit 0 to 9 in a corresponding desired output from the neural network. So E equals NP of zeros, 10, 1, so it would be 10 zeros, 1 dimensional. E of j equals 1.0. There's your answer. So we literally just load the data. So I've run this previously. I can run it again for the video, but I mean, I've run it previously. All the answers are already there, so we'll just go over what we have. So it just loads all the videos, and this is loading from TensorFlow right here. It's pretty easy to do it like that, so I just do it like that. I print them out just to make sure everything's cool. So this is the X-Train 60,000 28 by 28. The X-Test is 10,000 28 by 28. Y-Train and Y-Test are just 60,000 and 10,000 because those are just answers. So this is just extracting a random number just to make sure that they come out like they're supposed to. This is why I haven't squished them into a single line yet. They're still 28 by 28, as you can see, 25, 26, 27, 28, 25, 26, 27, 28. And when you have them like this, they're 28 by 28 pixels, and they form a handwritten digit. So if I were to run this all and then change this, it would give me, a random digit. So I just did this to make sure it was working. So I have the shape. I load those data wrappers, and then I change, because I loaded them, I changed the shape. So now the shape is a straight line, which is what we want, and you see the answer is also a straight line. So this is the actual number itself. Instead of this, it is now one straight line, one dimensional by 784, and this is one dimensional by 10. And now we create a network object, 784 input, 50 hidden layers. No, not 50 hidden layers. Sizes, layers, 50 layers, 10 output, and then we fit it. So we fit it with the data. This is 10 epochs, 10 mini batches, the learning rate, and we set the test data. And as you'll see, this is exactly what I said would output, remember? So epoch 0. This is with random fitting, this first one. Very lucky. But then, as you see, immediately it goes way up. And then it comes up, and we get the best one, I think, is... It actually goes... Well, yeah, no. It goes up the whole time, I believe. So... We achieve, and I could still train more, but we achieve about 95.5% accuracy. Out of 10,000, we get 9,000. And then I just print out the weights real quick just to get a view of it. I mean, you obviously can't see all of them because it's a massive neural network. You could open it in a text editor. And then I fit it 2 more times. Doesn't get much better. I just use the evaluate function real quick. The weights, they're mostly the same. And that is my neural network. I'm very proud of it, and I do plan to add onto it. I plan to add more layers, more activation functions. I'm not planning on stopping machine learning, deep learning, artificial intelligence anytime soon. So I do plan on expanding my knowledge on the subject and making this, a powerful neural network. Thank you.